Oxidation and reduction reactions are also very, very important in organic chemistry and bioorganic chemistry. And again, we will explore more in detail oxidation and reduction reactions in future years. It can be useful to think of an oxidation in an organic reaction as gaining oxygen, or sometimes it's easier to see it as losing hydrogen. So an oxidation is a dehydrogenation. Your compound loses hydrogen and hydrogen atoms. And in the case of a reduction, sometimes it can be easier to spot when a reaction is a reduction by looking at the gaining hydrogen. When a compound gains hydrogen, then when an organic compound gains hydrogen, then that compound has gone through a reduction. So hydrogenation is a reduction process. Dehydrogenation, loss of hydrogen. Gaining hydrogen is a reduction. Losing hydrogen is an oxidation process. And that can be easier to see in an organic compound than when we think of typically as oxidation is loss of electrons, reduction is gain of electrons. That works well with inorganic compounds, but for an organic compound, often looking at oxidation as a losing hydrogen and a reduction as gaining hydrogen can make it easier to spot whether the compound is oxidizing or reducing. So you can think of oxidation states of the carbon taking into account how much hydrogen, how many hydrogen atoms are attached to that carbon. So if you have one carbon, it can be in the most reduced form, in which all the positions of the bonding to that carbon are occupied by hydrogens, and slowly losing hydrogen atoms until you end up with the most oxidized species you can have with one carbon atom, which is CO2. None of the positions is occupied by a hydrogen. And when you have more than one carbon, then the most reduced species will be the one in which both carbons are surrounded by hydrogens, except the bond that they share with each other, and that is slowly are losing hydrogen atoms in different ways. And you can see that you can have different ways in which that species can have fewer hydrogen atoms until you end up with the most oxidized species that you can have without breaking that bond between those two atoms, that is forming a carboxylic acid. So loss of hydrogen and gaining hydrogen and losing hydrogen can be a good way of keeping track of whether that carbon is reduced or oxidized. I'm going to ask you to stop the video now and have a look at these three reactions and try to identify whether they are an oxidation or a reduction. So stop the video now, please. I hope you stopped the video and had a go at the exercises, predicting whether these reactions are oxidations or reductions. Let's have a look at the first one. Between the two compounds, the difference is in this carbon. In this case, you have a carbon attached to a hydroxyl group, and in this case, you have a carbon as part of a carbonyl group. And I'm going to draw here, I don't know if you see it, the fourth bond of that carbon, which would be, we are not painting it, but it is there, would be a hydrogen. In this case, this carbon already has 4 bonds, so there is no hydrogen there. So that compound has clearly lost, that carbon has lost hydrogen from the reagent to the product. So this would be an oxidation. It has lost hydrogen, a hydrogen atom from the reagent to the product. If we look at the second compound or the second reaction, the changes happen in this carbon here. So we have a carbon that is originally a carbon in a carbonyl group. It's attached to a sulfur atom, and in the first step, the sulfur atom disappears. It's a thioester, and you form an aldehyde. that carbon has gained hydrogen. Here, it has no hydrogen atoms directly attached to it, and here it has one hydrogen atom directly attached to it. So this step is a reduction. That compound has gained hydrogen. And when we move from the aldehyde to the alcohol, again looking at this carbon here, which is here, from the aldehyde to the alcohol, that alcohol has gained an extra hydrogen atom. Here the carbon has only one hydrogen, here it has two hydrogens. So again, this is another reduction. So that particular carbon has gone through a double reduction process, has gained hydrogen in two steps. Both are reductions. What happens with the third reaction? Is it a reduction or an oxidation? Well, in both cases, the carbon is attached to various atoms. None of them is a hydrogen. There's no difference in the number of hydrogen atoms that are surrounding that carbon. That carbon has not gained or lost hydrogens. That carbon has not gone through an oxidation or reduction process. That reaction is not a reduction or an oxidation. It's just a substitution of an ester or an ester group, an oxygen, for a nitrogen, but not through an oxidation or reduction. Redox processes have a huge role to play in biological systems. And for example, we have the process of cellular metabolism. You have the oxidation of glucose, the carbons in glucose, the 6 carbons in glucose that get oxidized to produce CO2, water, and energy. And on the other hand, you have the process of biosynthesis, the fact that you can reduce the carbon in the CO2, the 6 carbons that in 6 molecules of CO2 to produce glucose. So oxidation in one case, producing CO2 from glucose, and reduction in the other case, producing glucose from CO2, are both hugely important biological processes. The more reduced an organic molecule is, the higher the hydrogen content of that carbon, the more energy is released when it is oxidized. And this is why methane, for example, natural gas, is such a good fuel, because it's as reduced, that carbon is as reduced as it can possibly be. And I've got here some examples of the energy of liberated when in the reaction of those particular compounds to form CO2. And as you can see, the higher the number of hydrogen attached to that carbon, the more energy, those are all exothermic reactions, the more energy gets released. And that explains, for example, why fatty acids have more energy than sugars. Because in fatty acids, most of the carbons are in bonds with other carbons and hydrogens, so they are highly reduced, while in sugars, all the carbons will be attached to one hydroxyl group, so they are slightly, they are a more oxidized state. So the carbons that are in a more reduced state will liberate more energy when converting into CO2. Understanding organic chemistry and understanding bioorganic chemistry, so organic chemistry in a biological context, is hugely important. It helps us design new compounds, new pharmaceutical drugs. We can improve synthesis, so how we scale up a particular synthesis from a micro scale, from what you would do in the lab, to macro scale, to be produced in large quantities. It also helps us understand biological systems, and it helps us synthesize analogs to, for example, peptides or proteins, that helps us that helps us develop new medicines and new polymers of interest with interesting properties. And it also helps us improve our understanding of biological molecules, because we become better at synthesizing, purifying, and characterizing organic molecules, biomolecules, such as, for example, peptides or proteins or enzymes. So this is all from me. I hope it was useful. As usual, if you have any questions, just drop me an email and we can organize a tutorial. And thank you very much for watching.